Hi guys, welcome back to Chapter 7 and 8. This is going to be the last video content installment for 7 and 8, and this is going to be working with the sample proportion, and we're going to be doing similar things that we did with Z and T, but now we're going to be doing it with this new style of sampling distribution. So we'll be doing problems where we calculate a certain sample size. We'll be doing problems where we calculate confidence intervals, and that's that. And the thing that's going to be different about this is we're going to use the normal distribution, use the Z tables, but the way that we go about getting the information to put in the Z tables is a little bit different based upon this new distribution. So we're going to quickly go over this new distribution, and then we're going to work on some problems just as we normally would. So 7.3, the sampling distribution of the sample proportion. The distribution of all possible sample proportions is the sampling distribution of the sample proportion. If a random sample of S of size n is taken from a population, so this then the sampling distribution of the sample proportion is approximately normal if n is large, has a mean that equals p, and has a standard deviation that is equal to, and has a standard deviation. Okay, where p is the population proportion and p hat is the sampled proportion. So that p, with this p here, here we go. That's called p hat. This thing right here is p hat. So it's sigma p hat. And that's equal to p times 1 minus p over n, and the square root of all of that. Okay, so the way that this distribution is going to work is we're going to assume, we're going to assume that we know a population proportion, and that we then use that to calculate a standard deviation for p hat. And then we're actually going to run a sample and get a p hat. Okay? And then we're going to use these to come up with confidence intervals and make assumptions about population proportions and sample proportions and all that good stuff. So this is how we would do a confidence interval. P hat is going to kind of equate to like our x bar. P hat is going to be our sampled proportion. So like say we have like a sample of 1,000, n equal 1,000. If we come up with a data points that qualify, say 300 data points qualify, then p hat is going to be 300 over 1,000, so 0.3, that sort of thing. Okay. This is the formula for the confidence interval. And this is our formula for determining a sample size. I'm not going to spend a lot of time kind of explaining this. If you guys would like to know more prior to me working through some problems, you're free to go to section 7.3 and sections 8.4. First 7.3 definitely, but just to learn about the population proportion and so on and so forth. But I'm just gonna yawning. I'm just gonna get into solving some problems, and I think you'll kind of understand what's going on as we solve these problems. So go ahead and refer to 6, 7, 8, and 9 in your worksheet, and we're going to start with 6. Okay. The Food Marketing Institute shows that 17% of two-person households spend more than $100 per week on groceries. Assume the population proportion is p equal 1.7. So that's an assumption. We assume something about the population. And a simple random sample of 800 households will be selected from the population. What is the probability? What is the probability that the sample proportion will be within plus or minus 0.02 of the population proportion. So this is saying we assume that 17% of two-person households spend more than $100 a week on groceries. Okay, we're going to be taking a big sample of 800, and now we're going to try to determine what the probability that p hat, that population, or the sample proportion that we get from the 800 sample is within 0.02 of what we assume the population is. So basically, we're wanting to know, is it within 0.15 and 0.19. Okay. So we're going to answer this just as we have before. And first, we're going to calculate what our sigma p hat is. Sigma p hat is equal to, let's go back to our formula. How do we calculate sigma p hat? Sigma p hat is equal to p times 1 minus p over n in the whole square root of that. So p, 1 minus p, all over n, square root of that whole thing. So 0.17, 0.83, 800, square root, and that is going to be 0.013281. So that's our sigma. So now if we want to know this likelihood, we're going to just run this calculation just the same as we would anything else, right? So we're going to find a z-score. So we're going to run the plus or minus 0.02. So we're going to say z of, the plus the 0.02 on the top divided by our sigma, 0.013281, and we're also going to do the minus, but we know that the plus or minus are going to work out as such. So this is going to give us 1.51 plus or minus 1.51. So we find the z-scores for we find the probabilities associated with the z-scores. So probability that z is less than 1.51 and the probability that z is less than negative 1.51. We find what those are on the table. And we get 0.9345, 0.0655, and then in order to determine that range, it's just 0.9345 minus 0.0655, and that gives us 0.869. Okay. And then what is the probability? What is the probability that the sample proportion will be within that same 0.02 of the population proportion if a sample size of 1600 is selected? So we do this the exact same way. So we figure out what our sigma p hat is. Okay, we figure out what our sigma p hat is. Okay, and it's just going to be 0.17 times the 0.83 all over 1600 now. And this is going to end up being 0.00939. And then our z values are going to correspond to plus or minus 0.02 all over 0.00939. 0.1939 plus or minus 2.13. Excuse me. This is a little bit of my sickness showing through. 2.13, z less than negative 2.13, 98, 34.01, 66. We minus those, and that gives us 0.9668. And then it says, within what range should the middle 95% of the sample proportions fall? Use a sample size of 1600. So now we are running a confidence interval. So we have C is equal to 1.96, right? We already know that because that's what our 95% confidence interval says. So what range are we looking for? So what we do is we have our Z formula. So our Z formula for the population and proportion or sample proportion is going to be Z is equal to P hat minus P all over sigma P hat. Okay? And we have all these numbers, I think, except for P hat. We're going to solve for P hat. So we say plus or minus 1.96 is equal to P hat minus the P that we're using in this problem, which is 0.17, all over the sigma P hat, given that we're using 1600 as n. So sigma P hat is going to be this 0.00939. And then if we solve for this, this is eventually going to give us the interval from 0.1515956 all the way to 0.1884044. Okay, number 7. Of 43 bank customers depositing a check, 18 received some cash back. Construct a 90% confidence interval for the true proportion of all depositors who ask for cash back. And then it also asks us to check the normality assumption. Okay. So let's just do the first part first. We'll check the normality like down here or something, so we'll put A down there. So the first thing that I would do is I would determine what P hat is. So P hat is just going to be this 18 over 43. Those who receive cash back, the sample proportion of people who got cash back. So that is 0.4186. Then we would just go to our confidence interval formula that we have on the PowerPoint slide. So P hat plus or minus Z of alpha half times the square root of P hat 1 minus P hat all over n. So we'll go ahead and write this down so that we have it. P hat plus or minus Z of alpha half times, see if I can remember it, P hat times 1 minus P hat all over n. Yes, okay. And this is going to give us 0.4186 plus or minus 90% confidence interval. What was the 90% confidence interval that we used? Or the z-score for that? That was going to be the 1.65. 1.65 times P hat. So 0.4186 times 1 minus P hat which would just be 0.5814 all over 43, and that's included in the square root. And that is going to ultimately give us, without me showing all the arithmetic, 0.294467 through 0.542733. So this is to say that we have 90% confidence that the true P, the true population proportion, is going to be between 0.29-ish and 0.54-ish. Okay? That's based upon this small sample size and the p-hat that we were given. Okay? Then it says check the normality assumption, and the normality assumption is, we also had that. We assume that it's normal if n is large. Okay? And so that would mean that each one of these has to, the p-hat times n has to be greater than 5, and then 1 minus p-hat times n also has to be greater than 5. So that's how we check the normality. So let's see. So p-hat 186 times 43 is equal to 18, and that is greater than 5. And 1 minus 0.4186 times 43 is equal to 25, which is also greater than 5. So assume normality. Okay, number 8, on to number 8. What sample size would be required to estimate the true proportion of American female business executives who prefer the title Miss with an error of plus or minus 0.025 and 98% confidence? Okay, so let's write down what we know. So this 98% confidence implies alpha equal to 0.02, and the error that we're looking at is going to be 0.025. And what else are we going for? Oh, so this was this is something that we didn't get to talk about, but this is for population proportion, and if we don't have a sample proportion given to us, so say we're in a situation where p-hat is not given to us, we assume p-hat is equal to 0.5. So that's what we're going to do here. So now we just go find our formula for sample size. So n is going to be equal to p times 1 minus p. The reason that we assume 0.5 is because looking at this formula, this p, 1 minus p, the way that that is greatest, that term, the p times 1 minus p is greatest, is at 0.5. Right, so we could say we had p equal to 0.3. 0.3 times 1 minus 0.3, or 0.3 times 0.7, is less than, always, by definition, is going to be less than 0.5 times 0.5. So we just assume that p is equal to 0.5, and then that's going to give us the largest n possible. Okay, so p times 1 minus p times z alpha half over e squared. All right, and that is going to imply n equal 0.5 times 0.5. Excuse me. Oh, 98% confidence. What was our number there? I think our 98% confidence was 2.33. So that's the z value that we're using. Again, we know this from an earlier video when we solved for it. And E is 0.025. We don't have to put the plus or minus in there because we're squaring this anyways, so it's going to turn into a positive number. And so then when we solve for this, we get 2171.56, and then we automatically round up regardless of whatever it is, 2171 or 2172. So we would need 2172 of a sample size in order to be able to predict business executives' p-value for those that prefer miss with an error of 0.02 and 98% confidence. Okay, and lastly, we're going to hit the last sample size one. What sample size would be needed to estimate the true proportion of students at your college who are wearing backpacks with 95% confidence and an error of 0.04? What concerns might you have? Might you have, and how you collect the sample data? Okay, so we'll answer both those questions, one at a time. Okay, looks like we aren't given p again, so we just assume p equals 0.5. Okay, and we know that the formula that we're going to be using is this n is equal to p times 1 minus p times z of alpha half all over e and squaring the whole thing. So we assume a p just because we're not given one, and we're going with 95% confidence. So 95% confidence would just be the z of 0.025, right? Because alpha is going to be 0.05 in that scenario, and so then alpha half is 0.025. So this z that we're looking at is going to be the 1.96 that we're used to using now, and the e that we have is given to us, so it's 0.04. And it looks like we have all that we need in order to solve our problem. So we're going to say n is equal to 0.5 times 0.5, because 0.5 is, 1 minus 0.5 as well. And then we've got 1.96, 0.04, all squared. That's going to break down to 600.25, which is roughly 601. And what concerns might you have in how you collect the data? I think, I'm not sure we really even need a solid answer to this question, but think about how you would collect this data. You would probably collect this data walking around campus. Is it more likely to have a person that's carrying a backpack that is walking around campus? Probably, right? As opposed to somebody who say you collected this at noon, noon on a Tuesday or something at the student union. You're more likely to see backpacks, I think, than if you were to collect it outside of your 5:10 to 6:25 class that you go to on Tuesday and Thursday nights. Because those people might be people that work, so presumably they drove there, and then maybe they don't have a backpack, maybe they're just bringing their book and a notebook to class. So that would be something that you want to think about and a concern on how you collect data. I'm not really sure why that question was posed in this problem. It's more of a logical question. It's more of something that's more about sampling, random sampling, that type of stuff. But, you know, we'll answer it nonetheless. So, all right, guys, this is going to conclude the content lesson portion of chapter 7 and 8. I'll probably be putting out a review portion. Please let me know if you have any questions. Ask them in the discussion. Ask them via email. I'll try to answer them as soon as possible. I usually reserve a day, but I'm generally quicker than that. On the weekends, I reserve 2 days, but I'm also generally quicker than that as well. Please let me know if you have questions. Homeworks are open and ready, and quiz is open and ready. And once I get up that chapter 9 content, then I will put the test up and we'll determine a date on that, and we'll be off to the races. So again, I encourage you guys to get working on the case. But yeah, get working on chapter 7, 8, and 9 as well. All right. Thanks so much. Until next time. Bye.